So let's take a look at this next section. We're going to get to a formula that we can use here. And this first part, I'm just kind of walking you through the algebra to get you to that formula. So follow along as best you can, but this is the most important part down here. So it says for any two events, A and B, we know that the probability of A given B, so from the previous page, our conditional probability formula meant that the probability of A given B was equal to the probability of A and B, I'm going to use that intersection notation, divided by the probability of B. And then it says if these events are independent, what do we know? We know that the probability of A given B, so from right up here, if the events are independent, we know that the probability of A given B is equal to the probability of A. So that means I can replace this with the probability of A. So put the equations together from step 1 and step 2 here. So the probability of A intersect with B divided by the probability of B is equal to the probability of A. Because notice what I'm doing. Both of these represent the conditional probability. If the events are independent, step 2 is true. So if I tell you they're independent, step 2 is true, and I can put those two things together. And so equation 3 is, I'm not sure what they're looking for here, but what I want you to do is I want you to think about solving this equation that I have here, solving this equation for this numerator expression right here. So algebraically, how would I solve this equation? Well, we would take the probability of B and we would multiply it to the other side. So that gives us our formula for independent events. So if I tell you that A and B are independent, or you know they're independent because of the nature of the events, we can compute the probability of A and B. I'm going to use that notation. Remember, this means and. So I'm going to start using that notation. Probability of A and B can be found by doing the probability of A times the probability of B. So this is the important part that you want to pay attention to. If you know the events are independent, the probability of A and B can be found by doing the probability of A times the probability of B. Now, the next example on the next page, this was actually in the previous lesson, and we got to the bottom. I skipped it because we hadn't learned what we needed to learn. Here's what I was talking about. So let's look at this example. So it says, in Calculus AB, there are 45 multiple choice questions. Find the probability of guessing one question correctly. So if you may recall, it doesn't say it in the question, but there were 5 choices for each question. 5 choices for each question. So the probability of getting one question correct would be 1 out of 5. What would be the probability of getting 2 questions correct? So here's the way you want to think about this. Are these independent events? In other words, assuming you're totally guessing and making random guesses, if the probability of getting the first question right, does that have any influence on the probability of getting the second question right? Assuming the questions don't have anything to do with each other, they're not related in concepts, or you're just guessing and they're completely unrelated, these would be independent events, right? The probability of the first one correct has nothing to do with the probability of guessing the second one correct. So the probability of getting 2 questions correct, we could think of it as the probability of getting the first question correct and the second question correct. So that would be the probability of the first times the probability of the second. What I'm doing is I'm applying this formula right here. Because they're independent events, the probability of getting both correct would be the product of the probability of getting each one correct on its own. So for us, that would be 1/5 times 1/5 again. And I know that that would be 1 out of 25, but focus on what I'm doing here, the process, 1/5 times 1/5. How about the probability of getting 3 questions correct? Again, they are independent questions. So the probability of getting the first and the probability of getting the second and the probability of getting the third would be the product of those 3 probabilities. So that would be 1/5 times 1/5 times 1/5 again. How about getting all 45 questions correct? So if you're strictly guessing, again, the questions would be independent of each other. Getting one right would have no impact on getting the next question correct. So that would be what? That would be 1/5 times 1/5 times 1/5. How long do I need to do this? 45 times. So let's summarize that, and let's say 1/5 raised to the 45th power. So that would be a very, very small number. 5 to the 45th power would be a big number, which makes that a very small fraction. So you can think about that. If you strictly guessed on every question on a test with 45 questions, the probability of getting them all correct would be pretty slim. And that's what we're looking at here. So that's an example of independent events. All right, how about the next question? Suppose that 49.2% of babies born in the U.S. are girls. A couple has 2 children. So I want to just quick comment. This would be an empirical probability, right? Theoretically, half of the babies born should be girls and half of the babies born should be boys. But if I were to gather all of the data and I looked at, and it would be kind of tough to do, but let's say I took a sample and 49.2% of the babies in my sample were girls. That would indicate that, that it's an empirical probability because it's based on my observation. But let's just go ahead and go with the 49.2%. Determine the probability of selecting or picking a couple with 2 children. Determine the probability they both are girls. So again, are those independent events? Does the gender of the first baby have anything to do with the gender of the second? No, it would not. So this would just be the probability of the first being a girl times the probability of the second being a girl. Again, using this empirical probability, that would be 0.492. I'm changing the percentage to a decimal, so I move the decimal over 2 spots, times 0.492 again. And I don't have a calculator with me, but whatever that is, that would be our probability of both being a girl. How about the probability of getting a boy and a girl? So that would be, again, independent events, so I can multiply them. The probability of a boy times the probability of getting a girl. So using this empirical probability, the probability of getting a boy would be the complement of the getting a girl. So if I do 1 minus 0.492, that gives me the boy probability of 0.508 times the probability of getting a girl, 0.492. And again, I don't have a calculator with me, so I'm going to leave my value like that. But the point is, we're looking at and probabilities with independent events, so we can just multiply the 2 things together. Let's look at the last example. According to a recent survey, 48% of Target shoppers prefer to shop online rather than at their favorite brick-and-mortar Target store. So this is, again, an example of an empirical probability. It's based on an observation. We took a survey. Of that survey, 48% said they prefer to shop online. So this is an example of an empirical probability. Suppose 4 consumers are randomly selected with replacements. The reason that word is thrown in there is to show you that the population is going to stay the same, even though I keep selecting these people. The number of people to choose from is the same. But let's not worry too much about that right now. What is the probability that all 4 prefer to shop online? So think about this. Are the 4 people independent? Assuming they don't know each other, they're not related, they're not friends or neighbors. It's a random sample, so randomly selected people. So we can assume independence. So that would be the probability that the first person prefers to shop online, and I'm using O for online, and the probability that the second person shops online, and the probability that the third person shops online, and the probability that the fourth person shops online. So this is just like the questions above it. They're independent. So to get the probabilities, I'm just going to multiply each individual probability together. So assuming the probability for each one is 48% based on my sample, it would be 0.48 times 0.48 times 0.48 times 0.48. Sorry, I'm out of room here. And again, I don't have a calculator, but whatever that would be, 0.48 to the 4th power, if you want to shorten it up and write it that way. How about the probability that none prefer to shop online? So don't overthink this. Start with just the probability that one person selected prefers not to shop online. So the probability that one person does not want to shop online, so that's the complement of that they would want to shop online. So that would be 1 minus the 48%, which gives me 0.52. So the probability that all 4 don't want to shop online, again, those would be independent events. So that would be the probability of 0.52 times 0.52 times 0.52 times 0.52, whatever that probability ends up being. So to sum it up here, whenever you see the word and, or you're asked about multiple events happening at the same time, you want to ask yourself if those are independent events. And if they are, usually that's indicated by seeing the word random, like randomly selected people. or just in your own knowledge, if you think about something like flipping a coin and then rolling a die, those would be independent events. To find the probability of and events occurring, you're just going to multiply and use the independent event rule.